Alright, today we're going to have a look at the key differences between the concept of differentiation and then the idea of integration. So we've been introduced to the idea of differentiating for quite a while. We saw it in halfway between in the middle of last year in Year 11 Advanced, and we learnt that if I've got a function f of x, I can differentiate it by using our first principles, which is our f of x plus h minus f of x on h, and then we take that limit as h approaches 0. And then we learnt the different strategies to differentiate these different functions, like the product rule, the quotient rule, and the chain rule. So if f of x is our function, we can differentiate it and get f dash of x. But we've been introduced to this idea of integration and the fact that if I want to go back to where I started, I can do the opposite of the rule. So I know, for example, that if I were differentiating x to the power of n, well, I bring down the power and then subtract 1 from the power, so n times x to the n minus 1. But what if we wanted to go back to where we started? We wanted to go back to x to the n. Well, what we would have to do is we need to get rid of this minus 1. So we're going to add 1 to the power. That gets us x to the n. But there's still an n there. And we want to need to divide by n to get rid of that n. So what we've done is we've done the opposite of what we call the power rule. Instead of taking down the power and subtracting 1, we divide the new power and add 1 to the power. So inherently, integration is the opposite of differentiation, and it's that premise that is very important when we are solving more complex problems, that the opposite of differentiating is integrating, the opposite of integrating is differentiating. So what I thought we would do in this video is that I thought we would get a bunch of functions and we're going to differentiate it and integrate it. So let's say I had the function x squared and I wanted to differentiate it. We know that I can bring down the power and times it and subtract 1 from the power. So d by dx of x squared is equal to 2x. But what if I wanted to integrate it? The integral of x squared dx. Well, the integration rule tells us that we add 1 to the power and divide by the new power. Okay. Question number 2. Let's say I had 5x to the minus 7. Let's have a go at differentiating that. So d by dx of 5x to the minus 7. Well, we bring down the power, 5 times minus 7, and we subtract 1 from the power. 5 times minus 7 is a minus 35, x to the minus 8. What if we wanted to integrate it though? So let's say we wanted to find the integral of 5x to the minus 7. Well, when I've got this idea of an integral, we've got our integrand, which is the expression in the integral. We can just bring out the constant and integrate that there. And we really are doing that when we're differentiating and we're multiplying it in the last step. And we've got to put a dx, of course. The dx is saying, hey, I'm differentiating with respect to x. So the integral, we add 1 to the power and divide by the new power. So our answer is minus 5 on 6, x to the minus 6, and of course plus c. Again, don't get me started on, I hate that you lose a mark when you don't put a plus c, but it's just how it is. Let's say number 3, I think this is. Let's say I had the function x e to the x. And I wanted to know how to differentiate something like that. So part 1, let's differentiate x e to the x. Well, the product rule tells us that we differentiate the first thing, times it by the second thing, and then add the differentiation of the second thing and times it by the first thing. And we put it over the second thing squared. Again, we need to try in extension maths, move away from the idea of u's and v's and think about conceptually what's happening. So we differentiate the first thing. We differentiate we differentiate x and we get 1. Times that by the first thing, so 1 times e to the x. And we differentiate the second thing. If you differentiate e to the x, you get e to the x. So it's e to the x times by x. Right. So the differentiation of x e to the x is e to the x plus e to the x times x. In other words, we could say it's e to the x plus 1 if we factorized. Now in extension 1 and in advanced, what they might do is go, hence, determine the integral of e to the x plus 1 dx. Oh, I think I've done that wrong. Yeah, no, integral of e to the x plus 1. Now in extension 1, I know I have shown you integration by parts, but in extension 1, normally we can't integrate this because here I've got the product of two functions and we can't integrate that. However, we're going to realize the inherent relationship between integration and differentiation, and that's the fact that they're opposites of each other. So if I differentiate this and go to here, when I integrate this, I go back to where I started. So the integral of this is x e to the x plus c, and that's from part 1. So those types of questions are really testing your knowledge of, hey, do I know that integration and differentiation are one in the same? Question number 4. Let's say I wanted to, or let's say we had the function ln of x squared plus 2x. Right, and let's say I wanted to differentiate it. D by dx of ln of x squared plus 2x. Okay. So, we should know by now that there is a rule when we differentiate the natural logarithm. And that's the fact that I differentiate what's in the brackets. So differentiate x squared plus 2x. That gets me 2x plus 2. And I divide by what's in the brackets, x squared plus 2x. And that is our answer there. So the differentiation of ln of x squared plus 2x is 2x on 2 plus x squared plus 2x. Now, they might say that in extension 1, they're going to say, find that differentiation. And then they might go, hence, determine the integral of x plus 1 on x squared plus 2x. Now, the problem with this question is when we integrate functions like this, we're trying to figure out what do I have on the bottom and what happens when I differentiate it. If I differentiate x squared plus 2x, that gets me 2x plus 2. Now generally, the integral is in the form of the natural logarithm if the power on the top is 1 less than the highest power on the bottom. Because when I differentiate this, I'm going to get x. So we're thinking, hey, it's probably in the natural logarithm form. But what we need to do is we want 2 lots of that on the top. So to do that, I need to divide by a half, or times by a half. So that gets me the integral of 2x plus 2 on x squared plus 2x dx, and we've got a half out the front. Now that's in the natural logarithm form. A half ln of x squared plus 2x. The reason that's true is because if I want to differentiate ln of f of x, I get f dash of x on f of x. So if I have an integral where I've got the differentiation on top of a function, well then I can integrate it and go back to the natural logarithm, and that's why that's true. Now it's expected that you are able to understand this and realize that the opposite of, again, and I keep going on about this, the opposite of integration, differentiation is integration, and it's expected that you can recognize these forms and go back to the original function that has been differentiated through integration. Let's have a look at, what are we up to? Question number 5. Let's integrate and differentiate sine of x. So the differentiation, we might actually change it to sine of x squared. Well, when we differentiate sine, the rule tells us we differentiate the brackets and times it by cos of the same thing that's in the brackets. That's our answer there. Let's say, though, I wanted to integrate it. The integral of sine of x squared, dx, of course. Well, that tells us we need to go 1 over the differentiation of the brackets, because the opposite of pulling this out and timesing it out the front when I differentiate is going 1 over the differentiation of the brackets times by cos of x squared. However, since the differentiation of sine is positive cos, the integral of sine is going to be negative cos, because we're doing the opposite. We're doing the opposite function, because if you then differentiate this, the differentiation of cos becomes minus sine, and that minus will cancel with the second minus here and become positive sine. Let's have a go at question 6. We want to differentiate and integrate cos, we might put a 2 out here just for fun, x squared plus 3x. Let's say we wanted to differentiate that. Well, again, we're going to leave the 2 for a second, multiply it by the differentiation of the brackets, and cos, the differentiation of cos is minus sine. Bring out the minus, 2 times 2x plus 3 times sine of x squared plus 3x. Let's say, though, we wanted to integrate that. So part 2, the integral of 2 cos x squared plus 3x dx. Again, we're going to pull out the 2 from our integrand and say 2 times the integral of cos x squared plus 3x dx. And of course, when I integrate, well, over integrate cos, I get positive sine. And it's 1 over the differentiation of the brackets, 2x plus 3. And of course, plus c. So the answer is 2 on 2x plus 3 sine of x squared plus 3x. Now, if you don't believe me, differentiate that and you'll get back to where we started. If we differentiate this and we put it at the top here, 2x plus 3, that's going to cancel with that. That's going to become a cos, and we're going to get back to where we started. Let's have a look at some areas under curves. So let's say I wanted to know the area under the curve of y equals x squared. Or we might make it a bit more. Oh yeah, we can have y equals x squared. And I wanted to know that. And we wanted to integrate from 0 to 4. Well, I know that when I integrate, it is the same as finding the area under the curve. So this would be, the area would be the integral from 0 to 4 of x squared dx. When I integrate x squared, we add 1 to the power, divide by the new power, and it becomes that. Of course, we substitute in 4, so 4 cubed on 3 minus 0 gets us 64 on 3. And of course, units squared. We must put units squared because it's an area and we don't really know what units we're in. What if I wanted to know, however, this area here in black? There's two ways of doing this. Way number one is maybe this is part 2 of a question and I wanted to know the black area and the red area. Well, we know that 4 to the power of 2 is 16. So this is a rectangle of length 4 and height 16. So 4 by 16 is 64. So I know that the whole area of this whole rectangle is 64, which means the black area is going to be the whole area of 64 minus the area we just calculated in red of 64 on 3. And that gets us 128 on 3. However, there is another way of calculating that. Because what I actually can do, and if I just copy this to a new page, is instead of integrating with respect to the x-axis, we can integrate with respect to the y-axis. So we can find the integral from 0, we've just found this is 16, of something dy. We're now integrating with respect to y. Now we know y is equal to x squared, which means x is equal to the square root of y. So we want to integrate the square root of y from 0 to 16. If we integrate a function, we add 1 to the power and divide by the new power. And of anything, 1 over a half is 2, so 2 y to the 3 on 2. Now if we substitute that in, 2 times 16 to the power of 3 on 2, we get 100 and... something's gone wrong there. So 128. We get 128. Something's gone wrong there. So 64. What's gone wrong there? 2 times 16 to the power of 3 on 2. Just bear with me, something's gone wrong there. So the integral from 0 to 16 of y squared, we add 1 to the power. Oh, yep, okay, that's my fault. Sorry, we divide by the new power of 3 on 2. And that becomes 2 on 3 there. There we go, and we get a 128 on 3 units squared. So 1 over 3 on 2 is 2 on 3. Now often, actually, when I integrate this, I am comfortable going from here straight to here. Because when you've got fractional indices, it's always just 1 over and you're always just flipping it upside down. Okay. Let's have a look at some other common integrals. So, in extension 1, again, in extension 1 has not, officially we don't know how to integrate by parts. I have shown you, and we're going to use that, and I expect you to use that to check your answers because it's very, very fast. However, in extension 1, they're going to go something like this. Determine the differentiation of x sine inverse of x plus the square root of 1 minus x squared. Okay, well, we know that the product rule, again, I hate using those words, but the product rule tells us that we differentiate the first thing, 1, times it by the second thing, sine inverse, plus we differentiate the first thing 1 over the square root of 1 minus x squared. So that's the differentiation, of the second thing, and times it by the first thing. Now to the side, if we want to differentiate 1 minus x squared to the half, we bring down the power, times it by the differentiation of the brackets, and subtract 1 from the power. So, if we have a look at that, the 2's will cancel, and we're going to have minus x over, that's a negative power, we put it on the bottom, the square root of 1 minus x squared. Now they kill each other, and we've got sine inverse of x. Okay. So, what that question is telling us is that the differentiation of x sine inverse of x plus 1 minus x squared is equal to sine inverse of x. So if we want to integrate sine inverse of x, well, we know the differentiation of this whole thing is sine inverse of x. So if I integrate, I have to get back to where I started. So this question doesn't require any thinking, the integration. I already know the answer. And that's the answer there. So, in a similar manner, if I wanted to differentiate something such as cos inverse of 2 minus x, well, the differentiation tells us we differentiate the thing in the brackets. If we just want to look at the basic differentiation over here, it's minus 1 over the square root of 1 minus x squared. And the formula tells us, and often we call it the reverse chain rule, but the formula tells us we differentiate the brackets. So differentiate 2 minus x, you get minus 1. That's going to kill that 1 up there and make it positive 1 over the square root of 1 minus the thing in the brackets squared. Let's expand that. 1 over the square root of 1 minus 4 minus 4x plus x squared, which becomes 1 over the square root of 4x minus x squared minus 3. So that's the differentiation there. So if we wanted to know the integral from 1 to 2 of 1 over the square root of 4x minus x squared minus 3, well, we already know that the differentiation of cos inverse of 2 minus x is this. So the integration of this is just going to be cos inverse of 2 minus x from 1 to 2. So that's going to be cos inverse 2 minus 2 is 0 minus cos inverse 2 minus 1 is 1. Cos inverse of 0 is pi on 2. Now cos inverse of 1 is 0. So the answer is pi on 2. Some other things that are quite important are we've got to, in these questions, think smarter, not harder. Often, if I want to know the integral from, say, minus 2 to 2 of the square root of 4 minus x squared dx. Now, soon we're going to learn how to do trigonometric substitution, and we can actually let x equal sine theta, and then we can go, or we can let x equal 2 sine theta actually, and we would simplify the square root and we would get 2 cos theta, and we'd integrate. We can't do that at the moment though. So we're going to realise that this is a function of a semicircle with limits from the radius 2. So we just want to know the area of a semicircle from minus 2 to 2 of a semicircle of radius 2. So we want this whole area here. The area of a circle is pi r squared. So the area is pi times 2 squared divided by 2, which is 2 pi. And that would be our answer. Some other things that we might want to know are, let's say, e to the x squared plus 2x plus 1, and we wanted to differentiate, and we might also integrate that. Okay, the differentiation of this is, well, we differentiate the power, 2x plus 2, and we times it by e to the x squared plus 2x plus 1. That doesn't change. Let's say I wanted to integrate that, e to the x squared plus 2x plus 1, and I wanted to integrate it. Well, instead of bringing down the power, we're going to put 1 over the differentiation of the power. 1 over that. 1 over 2x plus 2, e to the x squared plus 2x plus 1, plus c. Because if we differentiated that, we would bring that down here, 2x plus 2, that would die, and we'd be left with that, and that would be our answer. We might finish off this video with maybe we might do a quotient rule question. So let's say we wanted to differentiate 1 minus root 1 minus x squared on x. Well, let's quickly in red to the side differentiate that, 1 minus x squared to the half. Bring down the power, times it by the differentiation of the power, and go 1 minus x squared, subtract 1 from the power. Our 2's die, and we get minus x over the square root of 1 minus x squared. So the quotient rule tells us that we differentiate the first thing. We've just done that, x on the square root of 1 minus x squared. Take away, we differentiate the second thing. That gets us 1, times it by the first thing, 1 minus x squared, square root, over x squared. Let's simplify. Let's make this a common denominator. Minus x minus, if I times that up to there, the square root goes away, over the square root of 1 minus x squared over x squared. Let's bring down that denominator. On the top, we're going to have, and I think I missed something, our quotient rule tells us we differentiate the first thing and times it by the second thing, so that makes it an x squared. We differentiate that there, times it by the thing on the bottom, that makes that an x squared. Our x squareds will die, and we've got minus 1 on the top, over, let's bring that down to there, x squared root 1 minus x squared. Now let's say part 2 of this question said, hence determine the integral of 5 over x squared root 1 minus x squared dx. And it will say hence or otherwise. By otherwise, it's just saying, hey, there's probably another solution. Maybe integration, probably not. Maybe integration by parts would work here. I highly doubt it though. But hey, there's another solution, but hence is probably, in most cases, the easiest one. Now we notice that it's almost the same as this, but we actually want minus 1 on the top. So what we might do is, okay, let's bring out this 5. We're allowed to do that. That puts a 1 on the top. We're allowed to bring out constants out the front of our integral. That's fine. But if we want a minus 1 on the top, we're going to have to put a minus here and a minus there to cancel it out. So it's going to be minus 5. Let's look at what our original question was. That there. Minus 5. I know the differentiation of that is what I have in my integral. So if I integrate it, I get back to this. So it's minus 5 times the square root of 1 minus x squared over x and plus c, and that would be our answer. I might end with one of the questions that you, in the exercise, it's one of the harder ones towards the end, that asks you to use the reverse chain rule. So I might end with something like this. The integral of 1 over root x, 1 plus x. Now realistically in the HSC, again, this is a textbook, these are not HSC questions. In the HSC, they will tell you the U substitution to use. However, this exercise is trying to get you to think in terms of the advanced idea of the reverse chain rule. So let's go. Let U equal the square root of x. That means du is equal to a half x to the minus a half. We bring down the power and subtract 1 from the power, so 1 on 2 root x. So du is that dx. Now we want to, and the whole goal of U substitution is to get rid of this and replace it with that. Now I've actually almost got that. Let's split this up. I've got 1 over root x times by 1 on 1 plus x dx. And I might actually even change the order of this again. We've got that there and this here. We've almost got this here. We need a 2 down here, but to undo that 2, I need to times it by 2, and those 2's would cancel, so it really means the same thing. Now I can replace this with that there. And also from up here, we have this x and we want to replace it with u because now I've got a du here. So I know from up here that x is equal to u squared. So this is 2, the integral on 1 plus x is u squared du. So 2 lots of the integral. This is now a 10. It doesn't matter what letters down here because it doesn't have to be x, it can be whatever we want. So 2 10 inverse of u plus c. But that's not good enough as our answer because we know u is root x. And we're plussing c. Okay, I hope that helps. Thank you for listening.